Hello, linear motion. When we mention linear motion, we're actually talking about a one-dimensional motion, and this actually includes horizontal motion and vertical motion. And in this lecture, we will focus on horizontal motion. Few concepts we have to consider here is the first one is distance. Distance actually is defined as how far an object traveled during a motion. And distance, if we have city A and city B, you drive your car from A to B 100 kilometers right here. And actually the distance here, it's 100 kilometers. And if you drive your car back to city A, now the distance here is another 100 kilometers. So the total distance is actually D here equal to 200 kilometers. Now, as we can see from this one here, distance is always positive. It's actually accumulating distances. Just imagine your car odometer. Your car odometer actually accumulating distances over and over. So distance is always positive, will never be negative, and it doesn't matter actually if you go right, left, if you go back, it's just positive and it's a scalar quantity. Now, another concept we would like to consider here is displacement. And displacement is how much the shift from your original position. So if you drive your car, same example, from city A to city B, 100 kilometers, and you go back another 100 kilometers right here, you will see that the displacement is equal to the shift from your original position. So your original position is A, and you end up with A. So displacement is, in this case, it's equal to 0. From this, we can tell that displacement could be positive, negative, or even 0. And in displacement, we actually care about the initial and final position. We don't care about the path itself. So if you drive your car this way, it doesn't matter actually, as long as we care about the initial and final position. And in this case, the displacement is equal to 0. Imagine like you drive your car from home and go to different places and back to your home. The displacement in this case equal to 0. Now, let's just have this a quick example here. If we would like to compare like +2 and -4, which one is the bigger than the other one? Now, in mathematics, okay, definitely we'll mention that 2 is greater than -4. But when it comes to displacement, the situation is quite different. Let's have this case. If we have a wall like this one here, and there's some guy here standing two meters from this wall. There is another guy standing -4 meters from this wall. So the displacement for this guy is actually greater than the displacement for this guy, even if it's with the minus sign. The minus sign actually gives us the direction for this guy, not is the magnitude. The magnitude, it's just force, so this displacement is actually greater than this displacement. Now, this will lead us to the next concept, which is average speed. Now, average speed is defined as the rate of change of distance. So, average speed is defined total distance over total time. And as we mentioned before, total distance is actually scalar quantity and it's always positive. So average speed is always positive and it's a scalar quantity. And now if we have a runner runs from position A and to position B like 100 meters and go back to the same position another 100 meters. So the average speed for this person here equal to 200 meters over, now assuming that the time for this whole trip it's 20 seconds, so over 20, so the average speed it's 10 meter per second. Now let's define the average velocity. Average velocity is defined as the rate of change of displacement, so delta x over delta t. Now if this runner here, actually the average velocity for this runner it's equal to 0 because the displacement for this runner here starts from position A and end up at position A, so the displacement equal to 0. So the average velocity for this runner actually equal to 0 meter per second. Now let's have an example. Now a particle moves from position x equal to 5 meters to x equal to 10 meters and then x equal to minus 5 in 2 seconds. Find the total traveled distance during the entire trip, the displacement of the particle during the entire trip, and the average velocity, average speed. Now the total traveled distance, he moved from 5 to 10, and this is actually d1, which is equal to 5 meters. Then he moved from 10 to minus 5. This is d2, which is equal to 15 meters. So the total traveled distance d, it's actually equal to d1 plus d2. So it's equal to 5 plus 15, or it's equal to 20 meters. Now how much the displacement? Now when it comes to displacement, as I mentioned before, we actually care about the initial and final position. So this is the final position, which is minus 5, and this is the initial position, which is 5. So delta x actually is the displacement. It's equal to minus 5 minus 5, which equal to minus 10 meters. Now the average velocity during the entire trip is actually equal to delta x, which is minus 10 in this case here, over delta t, it's 2 seconds. So it's equal to minus 5 meter per second. Now the average speed during the entire trip equal to total distance, it's a 20 over 2, which actually equal to 10 meter per second. Back to our lecture here. One concept we would like to express here is constant velocity. Now, constant, it means a number. Okay, that includes zero. Constant, it's not there's no variable in the velocity here, or it's so constant. As an example for this one here, now if this is v, which is in meter per second, and this is t in seconds, constant, it means if this is 5 meter per second, now this is constant velocity here. At t equal 1, it's 5, t equal 2, it's 5, t equal to 10, it's also 5 meter per second. This actually example of constant velocity in the vt scale. Now, in the xt scale, xt in seconds and meters, okay, constant velocity can be represented as this line, like this one here. The change in position is constant with time. So the constant, in this case here, the velocity actually is constant. Another case in the xt scale, this is x in meters and t in seconds, is this one right here. Even if it crosses the time scale, it's also constant velocity. Take this example here. If we have these three situations, now A in the x meters, t in seconds, this is A, this is B, and this is C. Okay, which one of these three objects is the fastest? You might think that the A is the fastest, but because it's the steepest and it's positive. But actually, the steepest one is C, and since we ask about the fastest, it means we need the magnitude. So C is the fastest because it's the steepest one, and B is the slowest because it's less steeper than the other ones. Now, let's define back to the average velocity and average speed here. Now, average speed, which is 10 meter per second, we actually don't know exactly this 10 meter per second in what part of this whole trip. So in this first part, second part, middle of the trip, we don't know exactly how much 10, because the runner could be increasing his velocity or speed, and or could be decreasing his speed. So this is the average. What we really care about the instantaneous velocity, which is the velocity at an exact moment. That's actually what the police officer measured in using the radar. So the instantaneous velocity here or sometimes it's called velocity. No need to say instantaneous. V, in this case, it's equal to the limit when delta t goes to 0, delta x over delta t, or dx by dt. Now, this is the instantaneous velocity. Now let's have an example. The position of an object as a function of time is given by this case here, where x is in meters and t in seconds. Find the velocity of the object at t equal to 5 seconds. So we would like here to calculate the velocity or the instantaneous velocity. So we would like to derive this function with respect to time. So in this case, dx by dt equal to 2 minus 8 t. Now t here, it's equal to 5. So in total, the velocity or instantaneous velocity, it's 2 minus 40, it's minus 38 meter per second. What's the average velocity during the time intervals 1 and 2? So the average velocity, it's actually equal to x final minus x initial over t final minus t initial. Now let's calculate x at t equal to 2. Now we will substitute 2 seconds in this equation. You will see 5 plus 4 minus 16. So 5 plus 4, it's 9 minus 16, it's actually minus 7 meters. And x, when t equal to 1 second, it's equal to 5 plus 2 minus 4. And in this case here, it's 3 meters. Okay, now average velocity, it's equal to minus 7 minus 3 over 2 minus 1 is just 1. So it's equal to minus 10 meter per seconds. Back to our last concept in this lecture here is acceleration. Now, acceleration, when it comes to acceleration, there's no such thing called scalar or vector. It's just a vector quantity. So A equal to A measured in meter per second square, and it's defined as the rate of change of velocity. So acceleration A here equal to delta V over delta T. So average acceleration, it's equal to V2 minus V1 over T2 minus T1. And there is another concept, it's called instantaneous acceleration or acceleration, and this is A is defined as the limit when delta T goes to 0, delta V over delta T, or A equal to dV by dt, or the second derivative of position with respect to time. One last example here. The velocity of an object as a function of time is given by this one right here. Find where Vx is in meters per second and t in seconds. Find the acceleration of the object at t equal to 2. Since it's asked about the acceleration, it's actually we need instantaneous acceleration. So A in this case, it's the derivative of V with respect to time, which equal to minus 8 t. Now t it's equal to 2, so A actually equal to minus 16 meter per second square. Now what is the average acceleration during time interval 1 and 3? So we would like to calculate the average acceleration here. It's equal to V2 minus V1 over T2 minus T1. So V2 in this case here, when T equal to 3, equal to 3 minus 36. So it's equal to minus 33 meter per second. Now V1, when t equal to 1, it's actually equal to 3 minus 4, which is minus 1. So average acceleration here equal to minus 33 minus 1 over 3 minus 1, which equal to minus 32 over 2, which is minus 16 meter per second. That's it. Thank you.